The Pacific Ocean owes its name to a moment of calm. In 1520, after weeks of violent seas, Ferdinand Magellan sailed into open water so peaceful that he called it Mar Pacifico, the peaceful sea. The name endured. It appears on every modern map, but beneath that calm lies a geological system unlike anything else on Earth. A belt nearly 25,000 miles long circles the Pacific Ocean. Along its edges occur roughly 90% of the world's earthquakes and about 75% of its active volcanoes. Most of it is hidden beneath thousands of meters of water, where its movements pass unnoticed until the planet suddenly reminds us that they never stopped. In 2022, a submarine volcano in Tonga produced the largest atmospheric explosion ever recorded by modern instruments. The pressure wave raced across the globe, while an unusual tsunami traveled not only through the ocean, but through the atmosphere itself. In several places, the wave in the sky arrived before the wave in the water. Scientists had never witnessed anything like it with modern instruments. More than 60 years earlier, a single rupture beneath the coast of Chile sent destructive waves across the Pacific, reaching Hawaii, Japan, the Philippines, and California from one earthquake. Farther north, another fault has remained silent since the night of January 26, 1700. Along the coast of Oregon, drowned forests still mark the moment the land suddenly fell. Across the Pacific, centuries-old Japanese records describe an unexpected tsunami that arrived without any local earthquake to explain it. The two stories are separated by oceans and centuries. They are part of the same system, a system that has never stopped moving. Tonight, we descend beneath the Pacific to follow the hidden chain of earthquakes, volcanoes, ghost forests, and forgotten records that reveal why the most powerful geological engine on Earth has always been waiting beneath the surface. For much of human history, the continents appeared fixed and permanent, as though they had always rested where they now stand. That perception began to change only after generations of observation slowly revealed a deeper pattern. During the 19th century, naturalists noticed remarkable similarities between distant coastlines and matching fossils separated by entire oceans. Even so, the explanation remained elusive until the revolutionary understanding of plate tectonics gained broad scientific acceptance during the 1960s, revealing that Earth's outer shell is divided into enormous moving slabs known as tectonic plates. These plates never rest. They drift across the planet at speeds measured only over years, carrying continents, islands, and ocean basins with them. Around the Pacific, more than a dozen major and minor plates meet in an intricate arrangement. The Pacific Plate dominates the center, joined by the Juan de Fuca Plate, the Nazca Plate, the Cocos Plate, the Philippine Sea Plate, the Australian Plate, and several others. Their boundaries weave together into an immense geological framework that surrounds nearly the entire ocean. The Pacific Plate itself is the largest tectonic plate on Earth, covering approximately 103 million square kilometers, which is about 39,768,000 square miles. Its vast size gives it contact with numerous neighboring plates, and those encounters shape nearly every major geological event around the Pacific Basin. The boundaries differ from one location to another, yet most are united by one fundamental process known as subduction. Subduction begins when a denser oceanic plate meets another plate that is either lighter oceanic crust or buoyant continental crust. Unable to remain above, the heavier plate bends downward and descends into the mantle beneath it. This descent unfolds across immense spans of time, yet the contact between the plates is rarely smooth. Friction locks portions of the boundary together, while the surrounding plates continue their gradual movement. Stress accumulates year after year until the rocks can no longer resist, releasing energy as earthquakes that ripple outward through both land and sea. The descending slab also carries water-rich minerals into the deep interior. As pressure and heat increase, those materials help generate molten rock that rises toward the surface. Over countless generations, this magma builds volcanic arcs stretching across continents and island chains alike. At the same boundaries, the downward bending plate carves immense trenches into the ocean floor, marking some of the deepest landscapes our planet possesses. Earthquakes, volcanoes, and trenches therefore emerge not as isolated phenomena, but as different expressions of the same underlying motion. Not every boundary around the Pacific follows this pattern. In some regions, neighboring plates slide sideways past one another along transform faults, exchanging tremendous stress without one plate descending beneath the other. These contrasting boundary types connect into an almost continuous horseshoe surrounding the ocean, creating what has come to be known as the Ring of Fire, even though it is assembled from many distinct geological systems rather than a single, uninterrupted feature. Scientific publications first described this remarkable belt as early as the year 1825, although its true mechanism remained hidden until the plate tectonics revolution more than a century later. Today, its path crosses at least 15 nations, including Chile, Peru, Ecuador, Colombia, the United States, Canada, Russia, Japan, the Philippines, Indonesia, Papua New Guinea, New Zealand, Tonga, Fiji, and neighboring island regions. Their shared history of earthquakes, volcanic eruptions, and tsunamis is written not by chance, but by the steady movement of Earth's living crust. Long before the defining moment arrived, the volcano had already begun to alter the rhythm of the sea. During the closing days of December in the year 2021, the submarine volcano, known as Hunga Tonga Hunga Ha'apai, entered a period of intermittent activity. Small eruptions broke the ocean's surface, sending ash and steam into the air. Volcanologists watched the sequence with careful attention, yet the behavior remained within expectations for an active volcanic system. The island that had emerged only a few years earlier still appeared intact, standing as a temporary meeting place between fire from below and waves from above. Everything changed during the afternoon of January 15th in the year 2022. At approximately 15 minutes past 5 in the local evening, the volcano experienced a catastrophic caldera collapse. A caldera forms when a vast chamber of molten rock beneath a volcano is suddenly emptied, leaving the overlying ground unable to support its own weight. Instead of remaining in place, the roof of that chamber failed inward, releasing an extraordinary amount of stored energy in only a few moments. The initial blast displaced nearly 10 cubic kilometers of rock, ash, and seafloor sediment, which is about 6 cubic miles of material, beneath roughly 150 meters of seawater, which is about 492 feet. The collapsing structure allowed enormous volumes of ocean water to rush downward toward intensely heated magma. The encounter unfolded almost instantly. Water transformed into expanding steam with explosive force, amplifying the eruption beyond what magma alone could have produced. Some researchers later described this process as a magma hammer, an image that captured the repeated and compounding violence created as seawater continued flooding into the collapsing volcanic cavity. The eruption reached at least level 5 on the Volcanic Explosivity Index, placing it among the most powerful volcanic events of the modern era, and drawing comparisons with the eruption of Mount St. Helens in the year 1980. Yet one measurement stood apart from nearly every eruption ever documented. The ash column climbed between 57 and 58 kilometers into the atmosphere, that is nearly 35 to 36 miles, rising beyond the stratosphere and into the mesosphere. No volcanic plume had been measured at such an altitude since the great eruption of Krakatoa more than 139 years earlier. Across the islands of Tonga, ash drifted downward in dense layers until daylight faded beneath a gray sky. Fine volcanic particles settled across villages, roads, rooftops, and fields. Fresh water supplies became contaminated as ash mixed with rainwater stored in household tanks. Aircraft could not safely approach, and communication became increasingly uncertain as the eruption continued to reshape both land and sea. The island of Hunga Tonga Hunga Ha'apai itself almost vanished, formed when earlier eruptions joined two small volcanic islands into a single landmass during the year 2015. It had always existed on borrowed geological time. Following the collapse, only scattered remnants remained above the ocean's surface. Beneath the waves, the caldera floor dropped by more than 1,000 meters, which is about 3,281 feet, leaving behind an immense underwater depression where solid ground had recently stood. The consequences spread far beyond the immediate landscape. Approximately 80% of Tonga's population, nearly 84,000 people, experienced direct effects from ashfall, damaged infrastructure, contaminated water, or tsunami impacts. The submarine fiber optic communication cable linking the islands with the wider world was severed during the event, isolating the nation for days while information traveled only through limited satellite connections and maritime reports. Much of the international community understood only fragments of what had occurred until ships and aircraft finally reached the affected islands. Remarkably, the confirmed human loss remained limited to 4 lives. That outcome reflected decades of community preparedness, regular tsunami evacuation drills, and warnings issued before the largest explosion occurred. Against the immense scale of the eruption, those preparations became one of the few enduring structures that the volcano could not erase. The eruption of Hunga Tonga Hunga Ha'apai produced not one tsunami, but two. The last event, believed to have displayed a similar combination, occurred during the eruption of Krakatoa in the year 1883, long before modern scientific instruments surrounded the planet. In the year 2022, researchers were able to follow every stage of the phenomenon with extraordinary precision, revealing that two separate processes had unfolded at the same moment, each traveling by an entirely different path. The first was the familiar form of tsunami recognized throughout modern hazard planning. As the underwater volcano collapsed and enormous volumes of the seafloor shifted, water above the eruption site was displaced outward in every direction. Gravity pulled that disturbed water into a long-moving wave that crossed the Pacific in the manner expected after powerful submarine earthquakes or volcanic collapses. Forecast models calculated its progress using the depth of the ocean and the known behavior of long-wavelength tsunami waves. The second wave belonged not to the sea alone, but to the atmosphere above it. The immense explosion generated an atmospheric pressure pulse that expanded away from Tonga at roughly 1,127 kilometers per hour, which is about 700 miles per hour. Rather than remaining high overhead, this moving pulse continuously pressed upon the ocean surface beneath it. As it advanced across the Pacific, the atmosphere and the sea became linked through a process scientists now describe as atmospheric coupling. The pressure disturbance effectively nudged the ocean forward, creating a meteotsunami that reached distant coastlines sooner than conventional tsunami calculations had predicted. Barometric instruments around the world recorded the passage of the pressure wave with remarkable clarity. It swept across every continent, then continued around the globe multiple times before gradually weakening. Each circuit left behind an atmospheric signature that could be traced from station to station, revealing a planetary scale disturbance produced by a single submarine eruption. Along the coast of Japan, forecasting centers relied upon established travel time models that had successfully guided warning systems for many years. Those models assumed that the first significant waves would arrive only after the displaced seawater completed its expected journey across the Pacific basin. Instead, water levels began changing earlier than anticipated because the atmospheric pulse had already reached the coastline and transferred part of its energy into the ocean. Instruments detected the unexpected arrival before many researchers fully understood the mechanism responsible. A similar sequence unfolded along the coast of Peru, nearly 10,139 kilometers from Tonga, that is nearly 6,300 miles. There, energetic waves reached the shoreline before warnings could be broadly distributed according to existing expectations. 2 people lost their lives after the unusual arrival demonstrated that distance alone could not guarantee additional preparation time when the atmosphere itself became part of the event. For generations, tsunami warning systems had been designed around one central assumption. A powerful earthquake displaced water, seismic instruments detected the rupture, numerical models estimated travel times, and coastal communities received alerts based upon those calculations. The eruption in Tonga revealed that volcanic tsunamis could follow additional physical pathways that were not adequately represented within those systems. A rapidly moving atmospheric pressure wave could alter arrival times, amplify coastal effects, and create behavior that traditional earthquake-based models did not anticipate. In the months that followed, researchers began developing interim guidance for volcanic tsunami detection that incorporated atmospheric pressure observations alongside conventional, seismic, and ocean monitoring. Networks once focused almost entirely upon earthquakes started considering the atmosphere as another source of valuable warning information. Near Tofua Island, waves reached heights approaching 45 meters, which is about 148 feet, placing the local event within the technical category of a megatsunami at close range. The eruption had not rewritten the laws of nature. It had revealed that those laws were broader than humanity had previously understood. Nothing on the floor of the Pacific is meant to last. Beneath the immense weight of the ocean, the ground itself is engaged in an endless exchange where new crust is born, carried across the basin, and eventually returned to Earth's interior. The apparent permanence of the seafloor is an illusion measured only against the brevity of human history. Across geological time, it is a landscape in constant motion, forever renewing itself through a cycle that has shaped the planet for hundreds of millions of years. The journey begins along the East Pacific Rise, one of the fastest spreading mid-ocean ridge systems on Earth. Here, the crust slowly parts, allowing molten rock from the mantle to rise into the opening. As this material cools beneath the seawater, it solidifies into fresh oceanic crust. Year after year, the ridge adds new seafloor at speeds reaching approximately 15 centimeters annually, which is about 6 inches each year. Though the movement is almost imperceptible from one season to the next, the accumulation over millions of years reshapes an entire ocean basin. Once created, this young crust begins drifting away from the ridge. During that long passage, it steadily loses heat, becoming thicker, heavier, and more rigid. As its temperature falls, its density increases until gravity begins to favor a downward path rather than continued buoyancy. Eventually, the aging plate reaches one of the subduction zones surrounding the Pacific, where it starts another stage of its remarkable journey beneath a neighboring plate. Not every descent follows the same geometry. Young oceanic crust still retains warmth and buoyancy, causing it to slip beneath adjacent plates at relatively shallow angles. Older crust has spent far longer cooling beneath the ocean, becoming substantially denser. When this ancient crust reaches a trench, it often plunges steeply into the mantle, descending like an enormous stone disappearing beneath dark water. The angle of that descent influences the depth of earthquakes, the shape of volcanic arcs, and the behavior of the surrounding crust over immense spans of time. Across the western Pacific, where some portions of the Pacific Plate are among the oldest surviving sections of oceanic crust, these steeply descending slabs generate earthquakes at astonishing depths. Some occur beyond 600 kilometers below the surface, which is about 373 miles. At such extraordinary depths, the familiar process of brittle rock fracture can no longer explain the release of seismic energy. The surrounding pressure is so immense that the rocks behave differently from those nearer the surface. Within the descending slab, the mineral, known as olivine, gradually transforms into denser crystal structures as pressure increases. In certain conditions, part of the olivine remains temporarily trapped in a less stable arrangement called metastable olivine. When that unstable structure finally reorganizes into its denser form, the transformation happens rapidly, releasing stored energy through the surrounding rock. Rather than ordinary fault movement, these deep earthquakes arise from a sudden crystalline rearrangement unfolding far beneath the crust. The balance between creation and destruction is no longer equal. Around much of the Pacific, oceanic crust is currently being consumed at subduction zones more rapidly than new crust is produced along spreading ridges. The basin is therefore contracting, almost imperceptibly, as its margins slowly advance inward. Geologists recognize this as part of the Wilson cycle, the immense geological rhythm through which oceans open, expand, shrink, and eventually disappear before new ocean basins emerge elsewhere across the planet. This perspective transforms the age of the Pacific itself. Although the ocean appears ancient beyond imagination, its floor is comparatively young because it is continually recycled. The oldest surviving Pacific seafloor is approximately 180 million years old, while portions of continental crust have endured for nearly 4 billion years. The contrast reveals a planet that endlessly renews its oceanic surface, making the Pacific not simply the largest ocean, but the most geologically dynamic basin on Earth, where creation and destruction remain inseparable parts of the same enduring cycle. Far beneath every familiar current lies a place where the surface world seems unimaginably distant. Here, the long journey of an aging tectonic plate reaches its deepest expression. The Mariana Trench was not carved by a single catastrophe or formed within a brief chapter of Earth's history. It emerged through the patient descent of the ancient Pacific Plate as it bends beneath the Philippine Sea Plate, creating the deepest depression known anywhere on the planet. At the trench's lowest measured location rests Challenger Deep, descending approximately 10,935 meters below sea level, which is about 35,879 feet, or nearly 11 kilometers. That is nearly 6.8 miles. The figures themselves almost resist imagination. If Mount Everest could somehow be lowered into Challenger Deep, more than 1 mile of seawater would still remain above its summit. Even the tallest mountain on Earth would disappear beneath the ocean without reaching the surface. With such depth comes pressure unlike anything naturally experienced elsewhere on the planet. At Challenger Deep, the surrounding water exerts approximately 1,086 times the atmospheric pressure found at sea level. Another way to picture that immense force is to imagine roughly 50 fully loaded jumbo jet aircraft balanced upon every square inch of the human body at once. Steel bends under such conditions. Ordinary materials collapse. Yet the trench has endured these forces continuously for millions of years as the Pacific Plate continues its gradual descent into the mantle. The trench itself stretches approximately 2,550 kilometers in length, which is about 1,585 miles, while reaching nearly 69 kilometers across at its widest point, that is nearly 43 miles. Rather than forming a simple crack in the ocean floor, it resembles an immense curving valley whose walls descend into extraordinary darkness before disappearing beneath layers of suspended sediment. Every additional meter marks another step into an environment governed by conditions entirely unlike those at the surface. For many years, scientists believed such depths would be almost devoid of life. Sunlight never reaches the trench floor, and the crushing pressure appeared incompatible with complex organisms. Careful exploration gradually replaced those assumptions with direct observation. Living communities occupy even these extreme depths. Tiny shelled organisms called foraminifera settle across the sediment. Amphipods wander the seabed, searching for organic material drifting down from above. Sea cucumbers slowly cross the pale floor, while microbial communities thrive within the mud itself, extracting energy from chemical processes that continue beneath the sediment. That seafloor is not bare rock. It is covered by a remarkably soft layer formed from the compressed remains of microscopic marine organisms that have settled through the water column over immense spans of time. Each drifting particle adds another delicate layer to the growing blanket of biological sediment, creating a landscape built from countless generations of life that once floated far above. Human beings first reached this extraordinary depth during the month of January in the year 1960. Don Walsh and Jacques Picard descended aboard the bathyscaphe named Trieste to approximately 10,916 meters, which is about 35,815 feet. Looking through their small observation window, they described a seafloor that was not empty. One observation included what appeared to be a flatfish moving across the bottom, although later researchers questioned whether such a fish could survive under those conditions. Many decades later, during the year 2019, explorer Victor Vescovo descended once again, reaching approximately 10,928 meters, which is about 35,853 feet, aboard the deep diving vehicle called Limiting Factor. Among the remarkable geological features and living organisms, another discovery appeared unexpectedly familiar. A plastic bag and discarded candy wrappers rested upon the deepest known point of the ocean, carried there through pathways connecting even the most distant reaches of the sea with the activities of the surface world. The Mariana Trench is therefore not an isolated curiosity hidden beneath the Pacific. It is the natural destination of an oceanic plate completing one stage of an endless geological cycle, where the deepest place on Earth exists because the planet itself never stops reshaping its own foundations. At approximately 11 minutes past 3 in the afternoon on the 22nd day of May in the year 1960, the ground beneath southern Chile began to shift. The movement did not end after a few seconds, as most earthquakes do. It continued for nearly 10 full minutes, an almost unimaginable span during which the boundary between the Nazca Plate and the South American Plate ruptured across an immense distance. Scientists later estimated that the fracture extended between 600 kilometers, which is about 373 miles, and 1,000 kilometers, that is nearly 621 miles, making it the largest instrumentally recorded earthquake in human history. Its magnitude reached 9.5, a value that remains unmatched in the modern record. Magnitude is measured on a logarithmic scale, meaning each increase represents an enormous rise in released energy rather than a simple addition. The Valdivia earthquake therefore exceeded even other great earthquakes by an extraordinary margin. Estimates suggested that the total energy released was comparable to the simultaneous detonation of approximately 20,000 atomic bombs, similar in yield to the weapon used at Hiroshima during the closing months of the Second World War. In the city of Valdivia, then home to roughly 100,000 people, buildings did far more than crack. Entire structures folded downward as foundations failed beneath them. Survivors later described streets rising and falling in broad undulations, giving the unsettling impression that solid ground had briefly adopted the behavior of flowing water. Familiar landmarks disappeared into clouds of dust, while roads fractured and bridges twisted beyond repair. The effects extended far beyond the immediate region. Tremors spread across much of South America, reaching communities hundreds of kilometers from the rupture, which is about many hundreds of miles depending upon their distance from the epicenter. Instruments designed to monitor atmospheric conditions detected pressure disturbances as far away as Antarctica, reflecting the immense transfer of energy between the solid Earth and the surrounding air. The earthquake had become not merely a regional event, but a planetary disturbance measurable across multiple scientific systems. Along the Chilean coastline, the landscape itself changed within moments. Sections of the continental margin dropped by as much as 2 meters, which is about 7 feet. Communities that had once stood safely above the highest tides suddenly found themselves closer to the sea than they had been only minutes earlier. Harbors shifted, river mouths changed shape, and familiar shorelines no longer matched the memories of those who had lived beside them for generations. The downward movement of the seafloor also displaced an enormous volume of seawater. Within minutes, tsunami waves rising as high as 25 meters, which is about 82 feet, struck parts of the Chilean coast. Their arrival came too rapidly for organized warning systems, leaving many coastal settlements with little opportunity to respond before the ocean surged inland. The earthquake's influence did not end when the shaking finally ceased. Approximately 2 days later, the Cordon Col volcanic system, located around 200 kilometers from the primary rupture, which is about 124 miles, entered a new eruptive phase. Volcanologists concluded that the immense seismic disturbance had altered stresses within a magma reservoir already approaching instability, providing the final geological impulse needed for eruption. Estimating the human cost proved difficult because entire communities had been disrupted at once. Historical records indicate that between 1,600 and 5,700 people lost their lives within Chile alone. Approximately 2 million people were left without homes, representing nearly 1/4 of the nation's population at that time. Even decades later, the Valdivia earthquake remains more than a record of extraordinary magnitude. It endures as a reminder that when one segment of the Ring of Fire releases its accumulated strain, the consequences extend through land, sea, atmosphere, and human history together. The rupture beneath southern Chile ended, but the motion it released refused to remain where it began. Across the Pacific, An immense pulse of displaced seawater continued its journey with unwavering momentum, crossing entire ocean basins without regard for coastlines or national borders. The earthquake had lasted only minutes, yet the wave it created would spend the next day carrying its energy from one side of the planet to the other. The tsunami spread across the Pacific at speeds approaching 800 kilometers per hour, which is about 497 miles per hour. Far from land, however, almost nothing about it appeared extraordinary. Ships traveling across the open ocean often noticed little or nothing as the wave passed beneath them. Its height was commonly around 1 meter, which is about 3 feet, or even less, while its enormous energy remained compressed within a remarkably long wavelength extending across vast distances. The danger was concealed not by its weakness, but by the immense volume of water moving together beneath the surface. As the wave encountered shallower coastal waters, the character of its motion changed. The ocean floor slowed the front of the advancing wave, while the immense body of water behind it continued forward. Energy that had been distributed across great depths was forced upward, transforming an almost imperceptible swell into a rapidly rising wall of seawater. Coastlines, separated by thousands of kilometers, experienced the same physical process, each becoming another stage in the tsunami's uninterrupted passage across the Pacific. Approximately 15 hours after the earthquake, the first major impacts reached Hilo on the island of Hawaii. Waves climbed to nearly 10 meters, which is about 33 feet, overwhelming parts of the waterfront. Warning messages had reached many residents before the tsunami arrived, yet human experience had prepared few people for the unusual behavior of such waves. In several locations, the sea first withdrew from the shoreline, exposing areas normally hidden beneath the tide. Curious observers approached the receding water, unaware that a much larger surge was already advancing behind it. 61 people lost their lives during the disaster. Roughly 22 hours after the original rupture, the tsunami reached Japan, nearly halfway around the Pacific from its point of origin. Along portions of the Japanese coast, waves rose to approximately 6.3 meters, which is about 21 feet. 139 people were killed despite the enormous distance separating their communities from southern Chile. The earthquake itself had never been felt there. Only the ocean carried its message across the basin. The tsunami continued onward, reaching the Philippines, where 21 people lost their lives. New Zealand recorded damaging waves, as did the Aleutian Islands and portions of the California coastline. Each impact illustrated the remarkable efficiency with which the Pacific transmitted energy over extraordinary distances, linking nations through a single geological event that had begun many hours earlier on another continent. Even oceans beyond the Pacific registered its passage. Tide gauges in both the Atlantic Ocean and the Indian Ocean detected measurable oscillations produced by the tsunami, making the event the first globally recorded tsunami in scientific history. Modern numerical simulations have since demonstrated that the wave nearly completed a circuit of the planet before gradually losing enough energy to fade into the background motion of the sea. It reflected from coastlines, bent around islands, and continued outward whenever geography allowed another path. The earthquake also produced an entirely different phenomenon within Argentina. A lake located approximately 200 kilometers from the epicenter, which is about 124 miles, began oscillating in a rhythmic motion known as a seiche. Instead of traveling outward like a tsunami, the water repeatedly sloshed back and forth within the enclosed basin for many hours after the earthquake had ended. The consequences of the disaster reshaped scientific cooperation as well. During the year 1965, The Pacific Tsunami Warning Center was established to monitor earthquakes throughout the basin and provide earlier alerts to vulnerable coastlines. The Valdivia tsunami remains enduring evidence that the Ring of Fire ignores political geography. A rupture beneath one shore can become a shared event for every nation bordering the same ocean. Some of the most important geological discoveries begin not with a mountain or an instrument, but with a story that seems impossible to explain. For nearly 3 centuries, one such story waited patiently on opposite sides of the Pacific. Its fragments rested in distant archives, along rugged coastlines, and within memories passed from one generation to the next, each preserving only part of a much larger event. On the evening of the 26th day of January in the year 1700, the entire Cascadia subduction zone ruptured almost simultaneously. This immense fault extends for approximately 1,000 kilometers, which is about 621 miles, lying roughly 80 kilometers offshore, which is about 50 miles, from what are now Northern California, Oregon, Washington, and British Columbia. Modern geological studies estimate that the earthquake reached a magnitude between 9.0 and 9.2. The ground across the Pacific Northwest continued shaking for at least 5 minutes, perhaps even longer, as one of Earth's largest fault systems suddenly released centuries of accumulated strain. No European account recorded the catastrophe. Permanent European settlement had not yet reached that coastline, and the indigenous nations who lived there preserved their history through spoken tradition rather than written documents. As generations passed, the earthquake itself faded from scientific awareness, unlike later disasters measured by instruments and newspapers. This event left behind no obvious record for historians trained to search written archives. The mystery began to emerge only during the closing decades of the 20th century, when researchers studying entirely different forms of evidence noticed remarkable connections. Japanese historical documents described an unexpected tsunami. Forests along the Oregon coast revealed signs of a sudden environmental change. Indigenous oral histories remembered a winter night when the earth convulsed and the sea swept across entire villages. None of these accounts initially appeared related, yet together they formed pieces of the same forgotten narrative. Across several communities on Honshu Island, official records described unusual flooding during the night of the 27th day of January in the year 1700. Boats were damaged, homes were flooded, and coastal settlements experienced destructive waves. Yet no earthquake had been felt anywhere in Japan before the sea arrived. Japanese historical seismologists eventually gave the event a memorable name, the Orphan Tsunami, a wave that appeared to have no parent because no local earthquake could explain its existence. For almost 300 years, that description remained unsolved. Historians carefully preserved the documents, but no known earthquake matched the reported arrival times or wave characteristics. As computer models improved, geologists began comparing the Japanese observations with simulated tsunami travel across the Pacific. One potential source after another was examined. Earthquakes originating in South America, Alaska, and the Kamchatka Peninsula failed to reproduce the historical timing recorded in the Japanese archives. The remaining explanation pointed toward Cascadia. During the year 1996, researcher Kenji Satake and his colleagues published evidence demonstrating that a full rupture of the Cascadia subduction zone could produce a tsunami, requiring approximately 9 to 10 hours to cross nearly 7,500 kilometers of open ocean, which is about 4,660 miles. Working backward from the recorded arrival in Japan, the earthquake itself would have occurred during the evening of the previous day along the Pacific Northwest coastline. Independent lines of evidence had converged upon the same conclusion. Long before geology confirmed the event, indigenous communities had carried its memory across generations. Oral traditions among the Huayat and other coastal First Nations told of a powerful earthquake, followed by an immense ocean flood on a winter night. Entire villages disappeared, and many people lost their lives while they slept. Those accounts were never intended as scientific records, yet they preserved the essential truth of a catastrophe whose physical evidence remained hidden until historians, geologists, and ancestral memory finally spoke with one voice. While historians searched through centuries-old records across the Pacific, another archive waited much closer to the earthquake itself. It did not exist on paper or within libraries. It stood rooted along the coastlines of Washington and Oregon, where weathered trunks rose from tidal marshes like forgotten monuments. Their presence had puzzled visitors for generations, yet their true story would emerge only when geology and biology learned to read the landscape together. Among the scientists drawn to this mystery was the American geologist Brian Atwater. During field surveys along the Pacific Northwest coast, he repeatedly encountered clusters of dead cedar and spruce trees standing upright in places where healthy forests could no longer survive. Their bark had long since disappeared, their trunks had faded with time, yet they remained anchored in waterlogged ground. The pattern suggested that these forests had not slowly declined through disease or ordinary environmental change. Something sudden had transformed the land beneath them. These became known as ghost forests. They were the remains of ancient coastal woodlands whose roots had once grown in fresh soil above the reach of the tides. During a great subduction earthquake, however, the compressed edge of the continent can abruptly sink as accumulated strain is released. Land nearest the coastline may drop by 1 to 2 meters, which is about 3 to 7 feet, within only a few moments. Forests that had stood safely above seawater suddenly find themselves below the daily tides. The trees did not perish over many years. Saltwater flooded their roots almost immediately after the land subsided, preventing them from drawing the fresh water needed for survival. Entire stands died together across at least 90 kilometers of the Washington coastline, which is about 56 miles. Their simultaneous death left behind an unusually consistent geological signal, preserved not only in the trunks that remained standing but also within the annual growth rings hidden inside the wood. To determine exactly when the trees had died, researchers turned to specialists known as dendrochronologists, scientists who study tree rings to reconstruct past events. Every growing season adds another ring beneath the bark, creating a natural calendar extending through the lifetime of the tree. Samples collected from the ghost forests revealed that the outermost complete growth rings had formed during the year 1699. No additional season of growth followed. The trees therefore died sometime between the autumn of that year and the spring of the following year, narrowing the event to a remarkably brief interval. That interval matched the timing preserved within the Japanese accounts of the orphan tsunami with astonishing precision. Independent evidence separated by an entire ocean had converged upon the same winter season, linking drowned forests in North America with unexplained waves recorded across the Pacific. Additional clues rested beneath the ground itself. Scientists extracted long sediment cores from coastal marshes throughout Oregon, Washington, and British Columbia. Within those columns of earth, they found a repeating sequence: dark organic soil supporting ancient vegetation ended abruptly beneath a pale layer of sand carried inland by a powerful tsunami. Above that rested tidal mud deposited only after the coastline had permanently subsided below sea level. The sequence repeated across numerous sites, revealing a regional event rather than isolated local flooding. Far offshore, sediment cores recovered from the ocean floor west of Washington contained deposits left behind by submarine landslides triggered during the same period. Even beneath the sea, the earthquake had written another chapter of its history into layers of sediment awaiting careful examination. When Japanese historical records, ghost forest dendrochronology, buried coastal sediments, and offshore geological deposits were finally considered together, the evidence became overwhelming. The earthquake of the year 1700 was no longer an ancestral legend or an unexplained historical curiosity. It had become a documented geological event reconstructed across 3 centuries through independent lines of evidence that had patiently preserved its memory. Along the Oregon coast, the Nescoin Ghost Forest still emerges during exceptionally low tides, where hundreds of ancient Sitka spruce stumps continue standing in the surf, marking the last time Cascadia released its immense accumulated strain. There are landscapes that seem almost too calm to invite a second glance. Forests grow, rivers follow familiar paths, highways carry travelers each day, and cities continue expanding across ground that has remained still for longer than living memory. Yet beneath the Pacific Northwest, that long stillness is not the absence of motion. It is part of a geological rhythm measured not in generations, but in centuries. The earthquake that reshaped Cascadia during the winter of the year 1700 was not a singular accident. Evidence preserved beneath coastal marshes, offshore sediments, and ancient forests reveals that it belongs to a repeating sequence stretching back at least 3,500 years. Researchers have identified signs of no fewer than 7 immense ruptures that fractured nearly the entire length of the subduction boundary, each leaving behind remarkably similar fingerprints across the region. Those ancient events do not occur according to a fixed timetable. Instead, they follow a recurrence pattern ranging from roughly 200 to 500 years, with an average interval of about 240 years. Such figures describe tendencies rather than promises. They reveal how the fault has behaved across thousands of years without offering certainty about its next movement. Every cycle has unfolded under slightly different conditions, shaped by stresses accumulating deep beneath the coastline beyond direct observation. By the year 2025, updated projections prepared through the Federal Emergency Management Agency placed the Pacific Northwest approximately 325 years beyond the last complete Cascadia rupture. That span lies well within the upper portion of the historical recurrence range. Even so, geologists consistently emphasize that averages cannot predict individual earthquakes. The next great rupture could begin tomorrow, or it could remain absent for another 2 centuries. No reliable precursor has ever been discovered that could extend warning beyond the brief interval between the first arriving seismic waves and the strongest shaking. Should the entire fault rupture again, with a magnitude of 9 or greater, the ground could continue moving for 5 minutes or more. Modern communities now occupy terrain that remained sparsely populated when the last event occurred. Much of the region's infrastructure was designed before scientists understood the full behavior of the Cascadia subduction zone. Roads, bridges, utilities, schools, hospitals, and countless older buildings were not originally engineered with such prolonged motion in mind. Current emergency projections estimate approximately 13,000 deaths, 27,000 injuries, and nearly 1 million people displaced from their homes. Important transportation corridors could also suffer widespread failure. Portions of the primary interstate highway, extending through the Pacific Northwest, may become impassable, interrupting the movement of emergency responders, medical supplies, food, and fuel across a region already struggling with extensive structural damage. Along the coastline, another race would begin almost immediately. A tsunami generated by a full Cascadia rupture could reach parts of Oregon and Washington within 15 to 30 minutes. That brief interval leaves little opportunity for organized evacuation by vehicle. Emergency planners have therefore emphasized a remarkably simple response. Anyone who experiences prolonged, powerful shaking near the coast should move on foot toward higher ground without delay, because the earthquake itself becomes the warning. This distinguishes Cascadia from the more widely recognized San Andreas Fault. While the San Andreas Fault is capable of producing destructive earthquakes, its ruptures are generally confined to sections of the fault rather than the simultaneous failure of an immense subduction boundary. Cascadia possesses the capacity for a megathrust earthquake where nearly 1,000 kilometers of fault, that is nearly 621 miles, may break during a single event, generating a tsunami comparable in scale to the devastating disaster that struck northeastern Japan during the year 2011. Major cities including Seattle, Portland, and Vancouver all stand within the region expected to experience severe shaking. Coastal communities extending from Eureka in Northern California to the northern reaches of Vancouver Island occupy areas where tsunami inundation could follow soon afterward. The long interval since the last rupture has allowed thriving communities to flourish, yet the absence of recent catastrophe does not represent geological peace. It reflects centuries during which immense forces have continued gathering beneath the continent, patiently storing energy until the cycle begins once more. Far below the restless surface of the Pacific, beyond the reach of sunlight and far from passing ships, another landscape continues shaping the planet in ways seldom witnessed. The familiar volcanoes rising above coastlines represent only a small fraction of this immense system. Most volcanic activity within the Ring of Fire unfolds beneath the ocean itself, where eruptions continue almost without interruption, hidden beneath vast depths of seawater. Current surveys by the National Oceanic and Atmospheric Administration have confirmed more than 450 volcanoes associated with the Ring of Fire. Even that impressive total captures only features that have been identified and mapped. Countless additional submarine vents, volcanic ridges, and seamounts almost certainly remain undiscovered across the immense Pacific Basin. Every new expedition reveals landscapes that had existed for countless ages without ever appearing on a chart, suggesting that the true number of active volcanic structures beneath the sea is considerably greater than present records indicate. For centuries, these eruptions remained entirely beyond direct observation. That changed during the year 2006, when an exploration expedition from the National Oceanic and Atmospheric Administration recorded the first submarine volcanic eruption ever witnessed in progress at the volcano known as Northwest Rota 1. Cameras revealed glowing lava bursting from a vent beneath the sea. The molten rock encountered cold seawater almost instantly, cooling so rapidly that it solidified into rounded forms called pillow lava. Each new pulse added another layer, preserving a process that has been constructing the ocean floor for hundreds of millions of years. Pillow lava has become the dominant rock covering the seafloor across much of the world. Instead of spreading into broad rivers, as lava often does on land, Molten basalt, released underwater, hardens almost immediately, swelling into overlapping, rounded masses. Layer upon layer, these formations accumulate across submarine ridges and volcanic slopes, gradually building the broad foundation upon which nearly every ocean basin now rests. Over immense spans of geological time, underwater volcanoes continue growing upward. Successive eruptions pile fresh volcanic material upon older deposits until towering seamounts emerge from the surrounding seabed. Some eventually rise several thousand meters, that is nearly 9,843 feet above the ocean floor. Only a small number continue climbing until they finally break through the surface and become islands, while countless others remain forever concealed beneath the waves. Not every volcanic island belongs to the same geological story. The Hawaiian Islands formed above a deep mantle hotspot rather than along the Ring of Fire. Many of the great island chains surrounding the Pacific, however, owe their existence entirely to submarine volcanism generated by subduction. The Aleutian Islands, the Mariana Islands, and the Tonga Island arc all began as underwater volcanoes, gradually assembled through repeated eruptions across millions of years until portions eventually rose above sea level. Occasionally, volcanic vents develop in comparatively shallow water, where rising magma meets seawater under conditions capable of producing exceptionally violent explosions. This style of activity is known as Surtsean volcanism, named after the Icelandic island of Surtsey, which emerged from the ocean during the year 1963. When seawater rushes into newly opened fractures and encounters intensely hot magma, it flashes into expanding steam with explosive force, fragmenting lava into ash and shattered rock before fresh material can accumulate. Among all known volcanic arcs, the Tonga Kermadec system contains the greatest concentration of submarine volcanoes ever identified. It was within this remarkable chain that the eruption of Hunga Tonga revealed how profoundly an underwater volcano can influence the atmosphere, the ocean, and distant shores. Yet that extraordinary event represents only one visible chapter in an almost continuous cycle unfolding beneath the sea. Most submarine eruptions occur at depths so great that no plume reaches the surface and no distant observer notices any change. Molten rock continues flowing, new crust continues forming, and ancient terrain is reshaped beyond ordinary human awareness. Long before forests covered the continents or the first animals walked upon land, this hidden construction had already begun. It continues today, steadily rebuilding the ocean floor in countless places, sustaining one of the oldest and most enduring geological processes on Earth. Not every revelation begins beneath an open sky. Some arrive in places where daylight has never reached, where the weight of the ocean presses upon ancient volcanic rock, and where the familiar rules of the living world gradually give way to something altogether unexpected. One such moment unfolded during the month of February in the year 1977, when a scientific expedition drifted above a remote stretch of the Galapagos Rift, a spreading ridge along the eastern Pacific shaped by the same restless forces that define the Ring of Fire. The research vessel Knorr carried instruments designed to examine the deep sea floor rather than search for extraordinary forms of life. As a deep camera system, known as Angus, moved across the volcanic terrain below, temperature sensors detected an unusual pattern. Water that should have remained close to 2 degrees Celsius, or 36 degrees Fahrenheit, showed pockets of unexpected warmth. The measurements hinted that heated fluids were escaping through fractures in the crust, carrying energy upward from the planet's interior. Curiosity guided the next step, Scientists descended in the research submersible Alvin toward the source of those rising waters, expecting to encounter interesting geology and little else. Instead, they entered a landscape unlike anything anticipated by existing scientific understanding. At a depth of approximately 2,450 meters, that is nearly 8,038 feet, the volcanic seafloor supported dense communities of living organisms gathered around openings where mineral-rich fluids streamed into the surrounding ocean. Great clams rested upon the rocky ground, some approaching the size of dinner plates. Towering tube worms emerged from pale protective casings that extended beyond 1 meter, which is about 3 feet above the surrounding sediment. Crabs wandered among the clustered colonies, while shrimp and fish moved through waters long believed to be nearly devoid of abundant life. Every creature occupied an environment untouched by sunlight, enduring immense pressure beneath the sea while flourishing in remarkable abundance. This discovery challenged one of biology's deepest assumptions. The deep ocean had generally been regarded as a sparse realm sustained by the gradual descent of organic particles from the illuminated waters far above. That slow rain of microscopic remains, often called marine snow, was thought to provide the limited nourishment available in the abyss. Rich ecosystems, filled with complex interactions between predators and prey, had never been expected upon the volcanic floor itself. The surprise reached beyond the remarkable animals. Few specialists in marine biology had joined the original expedition because the mission had focused primarily upon mapping geological features associated with seafloor spreading. Those who eventually examined the thriving communities found themselves confronting observations that existing scientific frameworks struggled to explain. The familiar relationship between sunlight and life no longer appeared universal. The answer emerged from chemistry rather than light. Heated water rising through the crust carried abundant hydrogen sulfide and other dissolved minerals from beneath the seafloor. Specialized bacteria had evolved the remarkable ability to capture energy directly from these chemicals through a process known as chemosynthesis. Instead of producing organic matter from sunlight, these microorganisms created it by harnessing chemical energy supplied by Earth's internal heat. They formed the foundation of an entire ecosystem sustained without any dependence upon the rays of the distant sunday. Every larger organism surrounding the vents ultimately depended upon these microscopic producers. Tube worms housed the bacteria within their own bodies. Other animals grazed upon bacterial mats or consumed creatures that relied upon them, forming complete food webs rooted in volcanic energy rather than photosynthesis. The heat escaping from the Earth's interior became the first link in a chain supporting an astonishing diversity of life. The discovery transformed far more than a single branch of oceanography. It demonstrated that thriving ecosystems could exist wherever suitable chemical conditions persisted, even in perpetual darkness beneath crushing pressure. One of the expedition's participants, Robert Ballard, later reflected that everyone remained without words, comparing the experience to processing a profoundly unfamiliar mathematical problem. Beneath the Pacific, the Ring of Fire had revealed not only how our planet reshapes its crust, but also how life itself can flourish by following paths once thought impossible. The discoveries beneath the Galapagos Rift had already transformed scientific understanding, yet the deep Pacific still held another remarkable secret. During the year 1979, researchers exploring the East Pacific Rise, another immense spreading ridge within the broader geological system surrounding the Pacific Ocean, encountered structures unlike anything previously documented. Rising from the volcanic seabed were towering mineral chimneys, releasing dense black clouds into the surrounding water, as though the ocean floor itself had become a landscape of slowly breathing mountains. These formations became known as black smokers. They developed where seawater seeped downward through fractures in newly formed oceanic crust, descended toward underlying magma, and returned upward after becoming intensely heated. Along that hidden journey, the water dissolved extraordinary quantities of minerals from the surrounding rock. When the heated fluid finally escaped through narrow openings and encountered the near freezing deep ocean, dissolved minerals crystallized almost instantly, gradually constructing tall chimneys from iron sulfide, zinc sulfide, copper sulfide, and many other mineral compounds. The escaping fluid reached temperatures exceeding 400 degrees Celsius or 752 degrees Fahrenheit. At the surface of the planet, water heated to such temperatures would erupt violently into steam. Yet the immense pressure found between 2,000 and 3,000 meters below sea level, which is about 6,562 feet and 9,843 feet, prevented boiling from occurring. Instead, the water remained in an intensely heated liquid state, carrying dissolved minerals in concentrations rarely found anywhere else on Earth. Each chimney grew grain by grain as fresh minerals settled from the venting fluid. Some eventually rose beyond 10 meters, which is about 33 feet in height, forming dark spires across the volcanic plain. Unlike mountains sculpted over millions of years by wind and rain, these structures could develop surprisingly rapidly, expanding as long as the underground circulation of heated water continued without interruption. Within the walls of a mature black smoker existed one of the most dramatic thermal boundaries found anywhere in nature. Temperatures approaching 400 degrees Celsius or 752 degrees Fahrenheit inside the vent could fall to near freezing conditions across only a few centimeters. That astonishing contrast created an environment where extremes existed side by side, separated by little more than the thickness of a human hand. Although such conditions would destroy most familiar forms of life, the outer surfaces of these chimneys supported flourishing communities of microscopic organisms. These remarkable extremophiles had evolved to survive temperatures and chemical environments once believed incompatible with life itself. Drawing energy from hydrogen sulfide and other dissolved compounds, they continued the process of chemosynthesis, first recognized only a few years earlier, extending the boundaries of what biology considered possible. Around the chimneys lived some of the ocean's most extraordinary animals. Giant tubeworms often exceeded 2 meters in length, which is about 7 feet, making them among the fastest growing marine invertebrates ever observed. Their vivid feeding plumes extended into mineral-rich water, gathering hydrogen sulfide that specialized internal bacteria transformed into nourishment. The worms themselves possessed no digestive system in the conventional sense. Instead, their partnership with microscopic life allowed them to flourish in an environment where sunlight had never penetrated. Over long spans of time, minerals settling around black smokers accumulated into extensive deposits known as seafloor massive sulfide formations. These deposits concentrated valuable metals including copper, zinc, gold, and silver in remarkable abundance. Their existence has drawn increasing commercial interest for deep ocean mining, while also raising difficult ecological questions. Scientists continue studying these fragile ecosystems, recognizing that disturbing them could erase biological communities that required thousands of years to develop and are still only beginning to be understood. Hundreds of black smoker fields have already been identified along the spreading ridges connected to the Ring of Fire, yet they almost certainly represent only a small portion of those that exist. Much of the global mid-ocean ridge system remains only partially mapped. Beneath the immense weight of the Pacific, hidden chimneys continue releasing heat from Earth's interior, building minerals, sustaining unfamiliar life, and quietly reshaping a world that remains largely beyond human sight. Nothing carried beneath the edge of the Pacific is truly lost. Each fragment of oceanic crust begins a descent that unfolds across spans of time so immense that continents shift, mountain ranges rise, and entire oceans change shape before the journey is complete. Drawn downward beneath the Ring of Fire, the aging seafloor enters the mantle, where it becomes part of a planetary cycle that steadily reshapes the chemistry and structure of Earth from within. For many years, this descent remained hidden beyond direct observation. That changed with the development of seismic tomography, a technique that interprets earthquake waves traveling through Earth's interior, much as medical imaging reveals structures inside the human body. Every powerful earthquake sends vibrations through the planet. As those waves encounter materials of different temperatures and densities, their speeds change in measurable ways. By combining thousands of such recordings, geologists have assembled detailed images showing immense slabs of ancient oceanic crust extending hundreds of kilometers beneath the surface. Some of these descending slabs appear to slow dramatically upon reaching depths of approximately 660 kilometers, which is about 410 miles. There, the boundary separating the upper mantle from the lower mantle presents an obstacle created not by composition, but by changing mineral structures. Under increasing pressure, the crystals making up the sinking rock reorganize into denser forms. This transformation can temporarily resist further descent, causing portions of the slab to flatten or linger before continuing their passage into deeper regions. Other slabs continue downward with remarkable persistence. Seismic images have revealed ancient oceanic crust at depths exceeding 2,000 kilometers, which is about 1,243 miles. Some interpretations suggest that fragments of even older slabs eventually approach the boundary, separating the mantle from Earth's outer core, approximately 2,900 kilometers below the surface, which is about 1,802 miles. There, material that once formed the floor of an ancient ocean may remain preserved long after every trace of that vanished sea has disappeared from the surface. As these slabs descend, another transformation unfolds within them. Oceanic crust forms beneath seawater and spends millions of years absorbing water into its minerals through countless fractures and chemical reactions. It also stores carbon dioxide within altered rocks and marine sediments resting upon its surface. Increasing pressure and temperature eventually force these substances back out of the sinking slab through a process known as slab dehydration, releasing fluids into the surrounding mantle. Those escaping fluids change the behavior of the mantle itself. Water lowers the melting temperature of nearby rock through a process known as flux melting, allowing portions of the mantle to become molten even though surrounding regions remain solid. The newly generated magma is less dense than the rock enclosing it, encouraging a gradual upward ascent through the overlying plate. After long passages beneath the surface, that magma may finally emerge through volcanic systems stretching around the Pacific Basin. In this way, water becomes the unseen engine sustaining much of the Ring of Fire. Without the water delivered downward by subducting slabs, far less magma would be produced, and many of the volcanoes defining this immense geological boundary would never have formed. Every eruption carries evidence of an earlier voyage that began on an ancient seafloor, far from the volcanic peak, where molten rock eventually reaches daylight. Carbon dioxide follows a similarly patient cycle. Released from descending slabs, it enters the deep mantle before gradually returning to the surface through volcanic emissions over millions of years. This vast circulation forms an essential part of Earth's long-term carbon cycle, helping regulate atmospheric carbon across geological ages. Even rocks exposed today upon distant continents sometimes preserve chemical fingerprints, proving they once belonged to oceanic crust buried deep within mantle wedges above ancient subduction zones. Their transformed minerals serve as enduring reminders that Earth's surface is never fixed, but endlessly renewed through a recycling engine operating far beneath every ocean. The boundary between ocean and continent can appear unwavering across the span of a human lifetime, yet beneath that familiar horizon, immense forces continue gathering beyond ordinary perception. Along the Japan Trench, where the Pacific Plate descends beneath the Eurasian Plate, centuries of motion accumulated until the afternoon of March 11, 2011, when the stored strain was released in a single extraordinary rupture that transformed both the coastline and the seafloor beneath it. At approximately 2:46 in the afternoon, a magnitude 9.0 earthquake began along a section of the subduction boundary, extending roughly 500 kilometers, which is about 311 miles. The rupture unfolded over approximately 6 minutes, not as one instant of motion, but as a cascading release spreading through the fault. During those minutes, parts of the Pacific seafloor shifted horizontally by as much as 50 meters, which is about 164 feet, an astonishing displacement accomplished in less time than an ordinary conversation. The greatest consequence did not arise from the sideways movement alone. As sections of the fault lurched upward and others settled downward, the shape of the ocean floor changed almost instantly. Resting above it was an immense column of seawater that had occupied the same space only moments before. Gravity immediately began restoring balance, and that adjustment became the birth of a tsunami. Energy passed from solid rock into the ocean with extraordinary efficiency, sending long waves racing outward across the Pacific Basin. For decades, Japan had prepared for precisely such a possibility. Coastal communities invested enormous resources in protective seawalls shaped by generations of experience and by careful studies of historical disasters. Many towns stood behind barriers reaching 10 meters, which is about 33 feet, 12 meters, that is nearly 39 feet, or even 15 meters, which is about 49 feet, above ordinary sea level. They represented remarkable achievements of engineering, designed according to the largest tsunamis preserved within historical memory. The approaching waves exceeded those expectations. In some locations, the water ultimately climbed to heights approaching 40 meters, which is about 131 feet above sea level. The sea crossed barriers that had seemed almost unimaginable in scale, continuing inland through neighborhoods, harbors, fields, factories, and roads. Structures that had endured earthquakes for generations were lifted, carried, broken apart, or swept back toward the retreating water as the coastline itself briefly became part of the ocean. Across the affected region, floodwaters spread over approximately 561 square kilometers, which is about 349 square miles, of coastal land. Entire communities disappeared beneath the moving water. Houses drifted beside fishing vessels. Automobiles turned slowly within powerful currents. Industrial buildings fractured as debris accumulated against them. The landscape became an ever-changing mixture of seawater, timber, steel, and sediment, reshaped minute by minute as the waves advanced and withdrew. The official record ultimately confirmed 15,899 deaths, while an additional 2,529 people remained listed as missing. Most of those lives were lost not during the earthquake itself, but within the advancing water that followed. The distinction revealed a profound truth about subduction earthquakes, because the greatest danger often arrives only after the strongest shaking begins to fade. Japan's earthquake early warning system performed exactly as its designers intended. Sensitive instruments detected the first arriving primary waves, the faster and less destructive vibrations that travel ahead of the strongest shaking. Automated alerts reached many communities within seconds, providing inland populations with valuable moments before the more powerful motion arrived. Yet for towns standing beside the coast, even half a minute could not overcome the speed of a tsunami already set in motion. The earthquake altered more than the shoreline alone. Careful measurements later indicated that Earth's axis shifted by approximately 17 centimeters, which is about 7 inches, while the length of a single day became shorter by approximately 1.8 microseconds. These changes were almost imperceptible within everyday life, yet they revealed that a great rupture along the Ring of Fire extends beyond any single nation, reaching into the motion of the planet itself. The most enduring consequences of a great earthquake do not always arrive with the first rupture. Sometimes they unfold through systems built with extraordinary care, where every safeguard performs exactly as intended until confronted by conditions lying beyond the limits of expectation. Along the northeastern coast of Japan, the events of March 11th, 2011, revealed how a force born beneath the seafloor could continue reshaping the world long after the shaking itself had ended. The Fukushima Daiichi nuclear power plant stood beside the Pacific, operated by the Tokyo Electric Power Company, and designed with multiple layers of protection against earthquakes and tsunamis. Historical records guided those defenses. Engineers concluded that the facility needed to withstand tsunami waves reaching approximately 5.7 meters, which is about 19 feet. That estimate reflected the greatest events documented across generations, and for many years, it appeared to provide a reasonable margin of safety. The earthquake arrived first. As the electrical grid failed, the reactors responded as designed. Automatic shutdown systems halted the nuclear reactions, and backup diesel generators immediately started, supplying electricity to pumps that continued circulating cooling water through the reactor cores. Although the ground had experienced one of the most powerful earthquakes ever instrumentally recorded, the essential safety systems remained functional during those first critical moments. Approximately 41 minutes later, the ocean arrived. The tsunami reaching the plant measured approximately 14 meters, which is about 46 feet, to 15 meters, which is about 49 feet, nearly 3 times greater than the height anticipated during the facility's original design. Water surged over protective barriers and spread across the site, flooding the buildings that housed the emergency diesel generators. One by one, those generators failed beneath the advancing seawater, and with them disappeared the electrical power needed to keep the cooling systems operating. Although the nuclear chain reactions had already stopped, another process continued without interruption. The fuel rods still produced decay heat, energy released naturally through the radioactive transformation of unstable atomic nuclei. This heat steadily accumulated inside the reactors. Without functioning pumps to remove it, temperatures rose hour after hour until portions of the nuclear fuel began melting. What had begun as a geological disaster gradually became a technological emergency, driven by the loss of cooling rather than by the earthquake itself. Over the following days, 3 reactor units experienced core meltdowns. Radioactive materials, including iodine-131 and cesium-137, escaped into the surrounding environment through a combination of controlled releases, damaged containment systems, and hydrogen explosions. Air, soil, fresh water, and coastal seawater all became part of an extensive monitoring effort as scientists worked to understand the scale and movement of the released contamination. The accident ultimately received Level 7 on the International Nuclear Event Scale, the highest classification available within that system. Only one previous nuclear accident had reached the same designation. Around the damaged facility, approximately 154,000 people left their homes within an exclusion zone extending 20 kilometers, which is about 12.4 miles. In the areas receiving the greatest contamination, some evacuation orders remained in place for years as extensive cleanup and monitoring continued. As investigators examined every stage of the disaster, an important pattern emerged. The reactors had survived the earthquake. Emergency shutdown systems had functioned correctly. Backup generators had started exactly as engineers intended. The decisive failure occurred because the tsunami exceeded the maximum wave height assumed during the plant's design. The natural event had not violated the laws of engineering. Instead, it had exceeded the historical experience upon which those calculations were based. The enduring lesson reaches far beyond nuclear technology. Every bridge, harbor, seawall, power station, and coastal community is ultimately shaped by assumptions about the greatest forces nature can produce. The Ring of Fire preserves no memory of those assumptions. Its processes follow rhythms measured across centuries and millennia, where the largest possibilities need not resemble the largest events preserved within human history, and where the next chapter is written according to geology rather than expectation. Mountains born from fire often appear permanent, yet each one is only the latest expression of a journey that began far beneath the ocean. As one plate descends beneath another, water carried downward from the ancient sea floor alters the surrounding mantle, encouraging rock to melt and rise again. That slow circulation eventually reaches the open air, where molten stone builds steep volcanic summits layer upon layer. These are stratovolcanoes, also called composite volcanoes. Their slopes formed from alternating deposits of hardened lava and compacted ash, each eruption adding another page to a story that may span hundreds of thousands of years. Unlike broad shield volcanoes, whose fluid basaltic lava spreads across the landscape in long, gentle flows, stratovolcanoes contain magma enriched in silica. That thicker magma resists movement, trapping dissolved gases deep within it. Pressure continues building until the surrounding rock can no longer contain it. When release finally comes, the eruption can unfold with astonishing force, sending ash, volcanic fragments, and expanding gases high into the atmosphere while reshaping the mountain itself in a matter of hours. Nowhere is this pattern gathered more densely than around the Ring of Fire. Across Indonesia, the Philippines, Colombia, New Zealand, Japan, the western coast of North America, and the towering Andes, chains of stratovolcanoes mark the boundaries where oceanic plates continue their descent into the mantle. Although each volcano possesses its own history and personality, they all owe their existence to the same immense cycle of subduction that has been reshaping the Pacific for countless ages. One of the clearest demonstrations arrived during the eruption of Mount Pinatubo in the Philippines. In the year 1991, the volcano produced an eruption assigned a volcanic explosivity index of 6. Roughly 20 million tons of sulfur dioxide entered the stratosphere, where the gas formed reflective aerosols that scattered a portion of incoming sunlight back into space. Over the following months, the average global temperature declined by approximately 0.5 degrees Celsius, or 33 degrees Fahrenheit, and that cooling influence remained measurable for nearly 2 years before gradually fading as the atmosphere slowly cleansed itself. Not every devastating volcanic disaster requires an exceptionally large eruption. In Colombia, Nevado del Ruiz erupted during the year 1985 with a volcanic explosivity index of 3, modest compared with many historic eruptions. Yet the heat generated by the eruption melted part of the mountain's glacial ice. Water mixed with ash and broken rock, creating volcanic mudflows known as lahars that rush downslope at approximately 50 kilometers per hour, which is about 31 miles per hour. Those fast-moving torrents overwhelmed the town of Armero, claiming approximately 23,000 lives and demonstrating that the greatest danger sometimes comes not from the eruption column itself, but from the landscape responding to it. Farther north, the Cascade Range stretches from northern California through Oregon and Washington into British Columbia. This chain forms the continental expression of the Cascadia subduction system, giving rise to peaks such as Mount Rainier, Mount Hood, Mount Baker, and Mount St. Helens. Among them, Mount Rainier rises to 14,411 feet, which is about 4,392 meters, and stands approximately 35 miles from Tacoma. Its slopes contain more glacial ice than any other mountain in the contiguous United States, while extensive hydrothermal alteration has weakened portions of its volcanic core. Geological studies indicate that even without a major eruption, large debris avalanches remain a credible hazard for valleys where hundreds of thousands of people now live. Along the western edge of South America, the Andes reveal the same process on an even grander scale. The mountain chain owes its existence to the Nazca Plate descending beneath the South American continent. Many of its highest summits are dormant or active stratovolcanoes, reminders that mountain building and volcanism remain inseparable expressions of the same deep movement. Indonesia completes this sweeping arc with approximately 130 active volcanoes, more than any other nation on Earth. Positioned where the Ring of Fire intersects the Alpide Belt, it has witnessed eruptions such as Tambora and Krakatoa, events whose effects reached far beyond their islands, altering weather, climate, and human history. Across every continent touched by the Pacific, these towering volcanoes reveal that the hidden motions beneath the ocean continue to sculpt the land above, raising mountains whose calm outlines conceal an energy measured not in human lifetimes, but in the enduring rhythm of the planet itself. Some volcanoes are remembered for the violence of a single eruption. Others command attention because they continue breathing through one human generation after another, never allowing those nearby to forget that the mountain remains awake. In the heart of central Mexico, Popocatépetl stands as one of those enduring presences, rising to 5,426 meters, which is about 17,800 feet. Since the year 1994, it has remained in a state of almost continuous activity, sending ash, steam, volcanic gases, and glowing fragments skyward in recurring episodes that have become woven into the rhythm of everyday life. Its position makes the volcano unlike almost any other along the Ring of Fire. Popocatépetl stands approximately 40 miles southeast of Mexico City, a metropolitan region home to more than 20 million people. It also rises only 30 miles from Puebla, a city whose population exceeds 3 million. Few active stratovolcanoes on Earth overlook such an immense concentration of people, transportation networks, industry, and agriculture. The mountain occupies a place where geological history and modern civilization exist within remarkably little distance of one another. For this reason, volcanologist Heather Handley has described Popocatépetl as a candidate for the most dangerous volcano on Earth when judged by population exposure. The assessment is not rooted in the expectation of the planet's largest eruption, but in simple arithmetic. Even a comparatively moderate event has the potential to affect millions because so many communities lie within reach of ash clouds, volcanic debris, and disruptions extending far beyond the mountain itself. Throughout the decades since its renewed activity began, the volcano has produced hundreds of small to moderate eruptions together with periodic, stronger episodes. Ash has repeatedly drifted across the Mexico City metropolitan area, coating streets, rooftops, fields, and reservoirs with fine volcanic particles. Aviation has also felt the consequences, as drifting ash presents a serious hazard to aircraft engines, forcing temporary changes to flight operations whenever prevailing winds carry material toward busy air routes. The geological record also reminds researchers that Popocatépetl is capable of considerably larger eruptions. A volcanic explosivity index of 5 lies well within its known history. During such an event, pyroclastic flows, fast-moving currents of intensely heated gas together with volcanic rock fragments could descend the mountain at speeds approaching 700 kilometers per hour, which is about 435 miles per hour. Temperatures within these flows may reach approximately 700 degrees Celsius, or 1,292 degrees Fahrenheit, carrying enough thermal energy to transform entire valleys within moments. Their tremendous speed leaves very little opportunity for movement once they have begun. The practical challenge of living beside such a volcano became especially clear during the year 2000, when authorities ordered the evacuation of approximately 50,000 people from surrounding communities. The operation required days rather than hours, revealing how difficult it is to guide large populations through mountainous terrain served by a limited network of roads. Successful evacuation depends not only upon scientific monitoring, but also upon transportation, communication, planning, and the willingness of communities to respond before conditions rapidly deteriorate. Even without a major eruption, widespread ashfall from a larger event could temporarily close Benito Juárez International Airport, the busiest airport in Latin America. Such disruption would extend well beyond the immediate slopes of the volcano, affecting commerce, travel, and supply networks connected to one of the region's largest urban centers. Fine volcanic ash behaves differently from ordinary dust, remaining suspended within the atmosphere while threatening aircraft systems and reducing visibility across broad areas. The mountain itself carries a name inherited from the Nahuatl language of the Aztec people, meaning smoking mountain. Long before scientific instruments measured its changing behavior, indigenous communities had already preserved generations of observation, recognizing that its recurring activity formed part of the natural order surrounding them. Beneath that enduring summit, the Cocos Plate continues descending beneath the North American Plate, the same deep process responsible for raising the Cascades, the Andes, and every great continental volcanic arc surrounding the Pacific. Here, perhaps more clearly than anywhere else, the mathematics of proximity reveals how the movement of unseen stone beneath the earth can shape the lives of millions living beneath a single mountain. Nothing along the Pacific remains fixed for very long, even when it appears unchanged from one human lifetime to the next. Beneath familiar coastlines and beneath islands scattered across the world's largest ocean, an immense slab of rocky crust continues a journey that never pauses. The Pacific Plate, the largest single tectonic plate on Earth, spans approximately 103 million square kilometers, which is about 39,800,000 square miles. It drifts steadily toward the northwest at approximately 7 to 10 centimeters each year, which is about 3 to 4 inches each year, carrying everything resting upon it across the face of the planet. This movement belongs not to imagination or distant geological history, but to the present moment. Networks of global positioning system receivers anchored across islands throughout the Pacific repeatedly measure their positions with extraordinary precision. Year after year, the recorded coordinates shift by exactly the amounts predicted by plate motion models. The ground beneath forests, cities, reefs, and volcanic peaks advances so gradually that no person can witness it directly. Yet the instruments reveal an uninterrupted voyage, unfolding every passing season. Every island, submerged mountain, and submarine volcano riding upon the Pacific Plate shares this motion. The Hawaiian Islands offer one of the clearest illustrations of this remarkable process. Their volcanoes did not emerge because the hotspot beneath them wandered across the mantle. Instead, the hotspot remained comparatively stable while the Pacific Plate passed overhead. One island formed above the rising column of hot mantle material, then slowly drifted away as volcanic activity shifted to the next location. Over immense spans of time, this produced a chain whose islands become progressively older from the southeast toward the northwest, preserving the direction of plate movement within the landscape itself. The same motion also determines where the ring of fire exists. Wherever the Pacific Plate converges with neighboring plates, dense oceanic crust eventually bends downward and begins descending into the mantle. Those descending margins become the birthplaces of powerful earthquakes, volcanic arcs, and deep ocean trenches. Because the plate itself continues moving, the geography of geological hazard also changes across millions of years. Regions that once stood far from active boundaries may eventually approach them, while others slowly drift away, reminding us that the familiar map of today represents only a single moment within a much longer planetary story. Not every boundary surrounding the Pacific operates through subduction. Along the western margin of North America, the San Andreas Fault marks a transform boundary where the Pacific Plate slides horizontally past the North American Plate. The relative motion proceeds at approximately 5 centimeters each year, which is about 2 inches each year. Although that pace appears almost insignificant within a calendar year, the accumulated distance becomes extraordinary across geological time. If the present motion continues for approximately 15 million years, Los Angeles will stand near the present latitude of San Francisco, carried northward through the patient persistence of plate movement. The forces driving this immense migration arise from deep within the architecture of the planet. One contribution comes from ridge push, created as newly formed seafloor emerges along spreading centers before gradually sliding away under the influence of gravity. An even greater influence comes from slab pull. As aging oceanic crust cools, it becomes denser than the surrounding mantle. Once subduction begins, the descending slab sinks under its own weight, pulling the remainder of the plate behind it like an anchor disappearing into profound depths. That realization transforms the Ring of Fire into something even more remarkable. The very trenches where plates vanish beneath the continents are also the engines sustaining their continued movement. Every earthquake, every volcanic arc, every newly opened fracture in the seafloor participates in a circulation that has endured for hundreds of millions of years. Across the Pacific, continents, islands, and mountains appear enduring when measured against a human lifetime, yet beneath them the Earth continues its patient migration, carrying entire worlds across the globe, one scarcely measurable step after another. Far below every trench that rims the Pacific, the journey continues long after the surface has forgotten where it began. Oceanic crust, descending beneath the ring of fire, does not simply vanish beneath the continents. It sinks into the mantle, carrying the memory of ancient seafloors downward through a realm that changes only across tens of millions of years. Every kilometer traveled marks another step in a transformation that unfolds beyond ordinary imagination, where familiar rock becomes something entirely different beneath extraordinary pressure. Modern science has learned to glimpse this hidden voyage through seismic tomography, a technique that compares the travel times of earthquake waves as they pass through the Earth's interior. Much as medical imaging reveals structures hidden within the human body, these waves expose regions that are colder or denser than the surrounding mantle. The resulting images often resemble immense curtains descending into darkness, long ribbons of ancient oceanic crust suspended within hotter material that slowly flows around them. Although no human eye has ever witnessed these depths directly, the behavior of seismic waves has revealed an astonishing portrait of motion occurring beneath every active subduction zone. As each slab continues downward, it eventually approaches a depth of approximately 410 kilometers, which is about 255 miles. There, one of the mantle's most abundant minerals, olivine, undergoes a remarkable transformation. Without changing its chemical composition, its crystal structure rearranges into a denser form known as wadsleyite. The transition releases heat while altering the way earthquake waves travel through the surrounding rock. That subtle change becomes visible within seismic observations, allowing researchers to identify one of the great internal boundaries separating different physical conditions inside the planet. The descent continues toward another profound threshold at approximately 660 kilometers, which is about 410 miles. Here lies the boundary between the upper mantle and the lower mantle. Many descending slabs appear to hesitate upon reaching this transition. Instead of continuing directly downward, they spread sideways, flattening into broad sheets that accumulate above the deeper mantle. Over immense spans of geological time, these collections have earned the evocative description of slab graveyards, vast repositories where fragments of long vanished ocean floors remain preserved far beneath the continents they once approached. Not every slab remains suspended there. Some retain sufficient momentum to penetrate the boundary, entering the lower mantle and continuing their gradual descent into conditions of even greater pressure and temperature. Seismic imaging has traced certain slabs to depths exceeding 2,000 kilometers, which is about 1,243 miles. Each discovery extends the known reach of plate tectonics farther into the Earth's interior, revealing that the influence of surface geology reaches much deeper than earlier generations of scientists imagined. Among the most remarkable events associated with these descending slabs are the deepest earthquakes ever recorded. Some occur between 600 and 700 kilometers beneath the surface, that is, nearly 373 miles to 435 miles. At such extraordinary depths, ordinary brittle fracture should no longer be possible because the surrounding pressures prevent rock from breaking in familiar ways. Instead, researchers now understand that these earthquakes most likely arise from another abrupt rearrangement of mineral crystal structures within the descending slab. Rather than conventional fault movement, the sudden transformation itself releases seismic energy, producing earthquakes in an environment once believed incapable of generating them. The slabs also transport far more than solid rock. Layer upon layer of ocean floor sediments descend together with minerals containing water and stores of organic carbon accumulated across ancient seas. As pressure and temperature steadily increase, these materials react, dissolve, and transform, enriching the mantle with an intricate mixture of chemical ingredients gathered from countless vanished oceans. Beneath every volcano, every trench, and every earthquake explored throughout this journey, the Earth's interior continues its patient work, drawing fragments of the surface into profound depths where they become part of a cycle that has shaped the planet for hundreds of millions of years and continues without interruption today. Water rarely comes to mind when imagining the immense forces that shape the Ring of Fire. Fire seems the obvious architect, rising from hidden depths and fountains of molten rock, while water appears only as the ocean resting above. Yet beneath every volcanic arc lies a partnership far older than any mountain, one in which water serves as the unseen guide that allows stone itself to melt. Without that hidden companion, much of the volcanic chain surrounding the Pacific would never have formed. Oceanic crust begins gathering water almost as soon as it is created. During countless years beneath the sea, seawater seeps into pores and fractures opened by cooling rock. At the same time, chemical reactions alter minerals within the crust, binding water directly into their crystal structures. Long before this ancient seafloor approaches a trench, it has become a vast reservoir carrying both physically trapped water and chemically bound water, preserving an invisible cargo gathered across millions of years beneath the ocean. When the oceanic plate finally bends downward into a subduction zone, increasing pressure and rising temperature begin to transform those hydrated minerals. At depths of approximately 30 kilometers, that is nearly 19 miles, to 40 kilometers, which is about 25 miles, the minerals gradually become unstable. Their crystal structures reorganize, releasing the water that had remained locked within them since the crust formed far from the continent. This transformation continues as the slab descends deeper into the mantle, unfolding across an immense vertical passage that extends far beyond the reach of direct observation. The released water enters an environment unlike anything found at the surface. Under such extraordinary pressures, it no longer behaves as an ordinary liquid or gas. Instead, it exists as a supercritical fluid, occupying an unusual state that combines characteristics of both. In this form, it becomes remarkably reactive, dissolving minerals and transporting chemical elements through surrounding rock with remarkable efficiency. Rather than remaining confined within narrow fractures, it spreads through portions of the mantle, carrying ingredients that reshape the chemistry of regions far removed from the descending slab itself. Eventually, this migrating fluid reaches the mantle wedge, the broad region of hot mantle resting above the descending plate. There, water performs one of the most significant roles in the entire volcanic cycle. It lowers the melting point of the surrounding mantle rock through a process known as flux melting. Rock that would otherwise remain solid under those temperatures and pressures instead begins producing magma. The result is not a consequence of additional heat alone, but of water changing the physical conditions under which melting becomes possible. The magma produced in this environment differs profoundly from the basaltic magma generated beneath spreading ridges far out in the ocean. As it rises through the crust, it becomes enriched in silica and grows increasingly resistant to flowing. Thick magma traps dissolved gases instead of allowing them to escape gradually. Pressure accumulates within the molten rock, until it eventually finds release through explosive volcanic eruptions that have become one of the defining characteristics of the Ring of Fire. Those dissolved gases include water vapor, carbon dioxide, and sulfur dioxide, each remaining mixed within the magma while deep underground. As the magma rises and surrounding pressure steadily decreases, the gases separate from the molten rock with increasing speed. Expanding bubbles force the magma apart from within, fragmenting it into ash, volcanic fragments, and incandescent clouds that race across landscapes during the largest eruptions. The remarkable violence associated with many stratovolcanoes ultimately begins with water carried downward into the mantle by an ancient slab of ocean floor. This understanding has reached far beyond our own planet. As spacecraft examine distant worlds and researchers identify hydrated minerals upon their surfaces, the relationship between water and volcanism has become an essential guide for interpreting planetary histories. Every subducting slab beneath the Ring of Fire reminds us that water does far more than shape oceans and rivers. Hidden within descending stone, it becomes one of the deepest creative forces inside the earth, transforming solid rock into molten pathways that have renewed the planet across hundreds of millions of years. Long before these coastlines carried forests, cities, or human voices, they existed only as rising towers of volcanic rock concealed beneath the Pacific. Their earliest history unfolded entirely below the waves, where countless eruptions slowly stacked layer upon layer of hardened lava upon the ocean floor. Each eruption added only a small measure to the growing mountains. Yet over millions of years, those hidden summits continued their patient ascent until, one day, they reached the surface and encountered open air for the first time. These newly emerged lands belong to a family known as volcanic arc islands. Their origin begins wherever one oceanic plate descends beneath another, allowing water released from the descending crust to generate magma within the mantle above. That magma rises through fractures, feeding submarine volcanoes whose repeated eruptions gradually construct immense seamounts. Eventually, some of those underwater mountains grow high enough to break through sea level, becoming islands that continue evolving through every succeeding eruption. The islands of Japan illustrate this long geological story with remarkable clarity. Rather than resting upon a single volcanic chain, the archipelago occupies a meeting place where several overlapping volcanic arcs have developed through interacting subduction boundaries. The arrangement recognized today began taking shape approximately 15 million years ago, yet the volcanic activity responsible for building its foundation stretches much farther into the geological past. Every mountain ridge and coastal plain reflects an accumulation of eruptions that occurred across spans of time so vast that individual volcanic episodes become almost impossible to distinguish from one another. Farther across the northern Pacific extends another remarkable chain. The Aleutian Islands sweep across approximately 1,900 kilometers. That is nearly 1,181 miles between Alaska and the Kamchatka Peninsula. Their arc contains approximately 57 volcanoes, each connected to the ongoing descent of the Pacific Plate beneath the North American Plate. Even now, the chain continues to grow. Fresh magma repeatedly rises from depth, adding new volcanic layers that slowly reshape coastlines already carved by wind, waves, and glacial ice. Toward the southwest, Indonesia presents an even more intricate landscape. More than 13,000 islands occupy a crossroads where the Ring of Fire intersects another immense tectonic system known as the Alpide Belt. The complexity of these interacting plates has created one of the most volcanically active regions anywhere on Earth. New eruptions occur many times throughout an average year, continually renewing portions of the landscape, while older volcanic rocks weather into fertile soils that support dense forests and extensive agriculture. The land itself remains geologically youthful, still receiving fresh additions from the mantle below. New Zealand offers another expression of the same enduring process. Across the North Island, the Taupo volcanic zone combines both subduction and crustal stretching, allowing magma to reach the surface through an active volcanic corridor. Approximately 1,800 years ago, one of the largest eruptions of the past 5,000 years transformed this landscape, spreading volcanic material across vast distances and leaving deposits that remain visible today. Yet, even such an immense eruption represented only another chapter within a story that has continued for millions of years beneath the island. A remarkable paradox accompanies every volcanic arc island. The forces responsible for creating these landscapes never truly depart once land appears above the sea. Earthquakes continue as plates remain in motion. Volcanoes continue receiving magma from depth. Offshore trenches preserve the same subduction systems that can generate powerful tsunamis. Creation and destruction proceed together, not as opposing events, but as inseparable expressions of the same planetary cycle. For the people who inhabit these islands, every coastline, mountain, valley, and geothermal spring traces its existence to processes unfolding far below the surface. Their nations were not established in spite of the Ring of Fire. They were assembled by it, lifted from the ocean through countless volcanic eruptions, then shaped continuously by the same deep forces that continue building the earth beneath their feet. One eruption and one generation of rock at a time. Far beneath the familiar outlines of continents lies a connected landscape that almost never appears on ordinary maps. The deepest trenches of the Ring of Fire are not scattered accidents of geology, but neighboring chapters within one immense system shaped by the same persistent force. From the Aleutian Trench in the northern Pacific, the chain continues through the Kuril-Kamchatka Trench and the Japan Trench, bends toward the Mariana and Philippine Trenches, then reaches the Tonga and Kermadec Trenches before similar subduction systems continue along the western shores of the Americas. Though separated by vast distances, they belong to a single planetary architecture carved through millions of years of descending oceanic crust. Every one of these trenches owes its existence to subduction. As one tectonic plate sinks beneath another, the descending slab bends the seafloor downward, producing immense valleys that mark the deepest portions of the global ocean. These depressions differ in shape and length, yet each records the same ongoing conversation between moving plates. They also shelter living communities that have adapted to conditions unlike those found anywhere else on Earth, where darkness, immense pressure, and scarce nourishment define every moment. For much of scientific history, the deepest parts of the ocean were assumed to contain very little life. Depths below 6,000 meters, which is about 19,685 feet, belong to a region known as the Haddle Zone. At such depths, pressure increases by approximately 1 atmosphere for every 10 meters, which is about 33 feet of descent. The crushing force seemed impossible for delicate cells to withstand, encouraging the belief that only the sparsest forms of life could persist within these remote environments. Careful exploration gradually revealed a different reality. Animals living within the Hadal Zone possess remarkable biochemical adaptations that protect the machinery inside their cells. Among the most important is a naturally occurring compound called trimethylamine oxide. As depth increases, the concentration of this molecule rises within the tissues of many trench organisms. It stabilizes proteins that would otherwise lose their functional structure under enormous pressure, allowing essential biological processes to continue where most familiar forms of life could never survive. Rather than resisting pressure through stronger shells or thicker bodies alone, these creatures have solved the challenge through chemistry unfolding at the molecular scale. The deepest trenches also preserve an unexpected connection with the distant surface world. Amphipods, small crustaceans resembling shrimp, collected from both the Mariana Trench and the Kermadec Trench, have been found carrying synthetic industrial pollutants within their tissues. These substances entered the ocean through human activity, attached themselves to sinking organic material, and descended through the water column over long periods before becoming incorporated into hadal food webs. Their presence demonstrates that even the greatest ocean depths remain linked to events occurring thousands of meters above. Research published during the year 2017 by investigators from Newcastle University confirmed that contaminants had reached places once believed almost entirely isolated from human influence. No direct contact carried these compounds into the trenches. Instead, they traveled through the continuous exchange of organic particles drifting downward from the productive waters above. Every fragment that settled upon the trench floor became part of an ecological pathway extending from the sunlit surface to the deepest habitats on the planet. Despite sharing a common geological origin, each trench supports its own distinctive biological community. The Japan Trench receives abundant organic material from highly productive surface waters, providing a relatively generous supply of nourishment for organisms below. The Kermadec Trench, beneath a region of the Pacific where nutrients are much less abundant, receives a different mixture of sinking material. Life has adapted accordingly, producing communities whose species, behaviors, and ecological relationships differ even at comparable depths. Across this connected trench system, the geology remains remarkably consistent, yet the living worlds shaped within each abyss reflect the unique character of the ocean far above, binding the highest waters and the deepest seafloor into one uninterrupted planetary cycle. Some parts of the Ring of Fire seem to move according to an even older rhythm, as though the machinery beneath the surface has chosen a faster pace without changing its purpose. Nowhere is that rhythm more evident than along the Tonga-Kermadec subduction system, where the Pacific Plate descends beneath the Australian Plate more rapidly than at any other known subduction boundary on Earth. Here the plates converge at rates reaching approximately 24 centimeters during each passing year, a speed that steadily reshapes the surrounding ocean basin while remaining almost imperceptible within the span of a human lifetime. The trench formed by this remarkable collision extends into one of the deepest places on the planet. Its greatest measured depth approaches 10,800 meters, which is about 35,433 feet, placing it second only to the Mariana Trench. The difference between them is astonishingly small on a planetary scale, separated by only about 135 meters, which is about 443 feet. Across such immense depths, the distinction between first and second becomes almost insignificant beside the extraordinary journey taken by the descending crust. Beneath the trench, the rapidly moving slab plunges into the mantle at one of the steepest angles observed anywhere within the Ring of Fire. Seismic imaging has revealed this descending plate extending deep below the surface like an immense ribbon of colder rock surrounded by the hotter mantle through which it travels. Its swift descent carries oceanic crust downward more efficiently than almost any comparable system, transporting minerals, water, and ancient seafloor into environments where pressure and temperature continually transform their physical structure. The consequences of this rapid motion reach upward as well as downward. Above the descending slab lies the greatest known concentration of submarine volcanoes on Earth. Much of this volcanic activity unfolds beneath thousands of meters of seawater, escaping direct observation while steadily reshaping the seafloor. New volcanic cones emerge, older structures collapse, and hydrothermal systems circulate heated fluids through fractured rock in an almost uninterrupted cycle. It was within this extraordinary volcanic province that the volcano, known as Hunga Tonga Hunga Hapai, produced its remarkable eruption during the year 2022, reminding the surface world that even largely concealed volcanoes can influence the entire atmosphere. The pace of subduction also leaves its signature within the pattern of earthquakes. Because the slab descends so rapidly, it carries material into the deep mantle with unusual efficiency, producing frequent earthquakes between depths of approximately 400 kilometers, which is about 249 miles, and 700 kilometers, which is about 435 miles. These events occur far below the levels where ordinary rock fracture would normally be expected, reflecting profound mineral transformations taking place inside the descending plate as it continues its passage into the Earth. For geologists, geophysicists, and oceanographers alike, the Tonga Kermadec region represents an extraordinary natural laboratory: fast subduction, abundant submarine volcanoes, steep slab descent, vigorous hydrothermal circulation, and persistent deep earthquakes combine within a single, interconnected system. Each process influences the others, allowing researchers to observe relationships that may appear only faintly in slower subduction environments elsewhere around the Pacific. The region has therefore become one of the most scientifically valuable places for understanding how the interior of the Earth operates across immense spans of space and time. Above this restless foundation rests the Kingdom of Tonga, an archipelago composed of 169 islands whose total land area measures approximately 747 square kilometers, which is about 288 square miles. Every island owes its existence to volcanism generated beneath the surrounding ocean. Earthquakes, tsunamis, and eruptions have shaped these landscapes for countless generations before written history, while the same deep processes continue lifting, altering, and renewing the islands today. In this distant corner of the Pacific, the boundary between solid land and the forces that created it remains remarkably thin, preserved by a subduction system that never truly comes to rest. The story stretches far beyond memory, beyond civilization, beyond even the oldest mountains still standing beneath the sky. The forces shaping the Ring of Fire have unfolded through spans of time so immense that entire oceans have appeared, transformed, and vanished, while the deeper pattern continued. In different arrangements and along shifting boundaries, the processes that define this vast tectonic system have remained active for at least 700 million years, carrying the planet through one chapter after another without interruption. The Pacific Plate itself might seem ancient, yet it is surprisingly youthful when compared with the history surrounding it. The oldest surviving portion of its seafloor is approximately 180 million years old. Almost none of the earlier Pacific seafloor remains because generation after generation has descended into surrounding subduction zones. Older oceanic crust was steadily carried downward, heated, compressed, and ultimately recycled into the mantle. The seafloor visible today is only the latest surface of an ocean whose previous foundations have almost entirely disappeared beneath the continents that border it. Geologists describe this recurring transformation through a concept known as the Wilson cycle, named after Canadian geophysicist John Tuzo Wilson. Ocean basins begin as continents gradually separate, allowing molten rock to create new seafloor between them. Over immense intervals, that ocean widens until new subduction zones develop around its margins. Once subduction becomes established, the balance changes. The ocean that once expanded begins to contract as its floor is consumed beneath neighboring plates. The Pacific Ocean has entered this closing stage, losing crust around its edges more rapidly than new crust is produced along the volcanic ridges crossing its interior. Measured across a single year, that change seems almost impossible to notice. On average, the Pacific Basin becomes approximately 2.5 centimeters narrower each year. Projected across hundreds of millions of years, however, that steady motion points toward a remarkable future. Many geologists propose that continued convergence will eventually eliminate the Pacific Ocean altogether, gathering today's continents into a future supercontinent called Amasia. Current models place that distant assembly roughly between 250 million and 300 million years from now, though the exact pathway remains one of Earth's continuing geological stories rather than a fixed destination. Evidence for these vanished oceans survives in unexpected places. Certain mountain belts preserve remarkable rock sequences known as ophiolites, fragments of ancient oceanic crust that escape descent into the mantle. Instead of continuing downward with the rest of the seafloor, these sections were scraped away and attached to continental margins during subduction. Today they appear high above sea level within mountain ranges extending from the Alps to the Appalachian Mountains. Their minerals preserve distinctive chemical signatures that allow geologists to reconstruct long-vanished oceans and trace plate movements reaching hundreds of millions of years into the past. The recent chapter of Earth's history tells a similar story. During the Holocene epoch, spanning approximately 11,700 years, the four largest volcanic eruptions all occurred around the Pacific Basin in Alaska, Kamchatka, Oregon, and Japan. Across that same interval, roughly two-thirds of all recorded volcanic events on Earth originated along the Ring of Fire. The pattern is so consistent that it reveals something fundamental about the planet itself. This immense chain of subduction zones is not merely one remarkable geological feature among many. It is the principal engine of Earth's surface volcanism across the span of human existence, while beneath every generation, it continues the patient work that began hundreds of millions of years before the first footsteps ever crossed the land. Even now, after centuries of exploration and astonishing technological progress, the greater part of this immense volcanic frontier remains beyond detailed human sight. The Ring of Fire shapes continents, mountains, trenches, and oceans, yet much of the sea floor beneath its waters is still known only through broad outlines. In an age when distant worlds have been photographed with remarkable clarity, the landscape hidden beneath the Pacific continues to preserve vast stretches of unanswered geography. One of the enduring ironies of planetary exploration is that more of the lunar surface and the surface of Mars has been mapped in fine detail than the floor of the Pacific Ocean. Water conceals what air freely reveals. Sunlight cannot penetrate the immense depths where the Ring of Fire carries out much of its work, leaving ships and instruments to assemble the hidden terrain piece by careful piece. Every expedition expands the picture, yet the complete landscape remains far beyond present knowledge. The broadest global maps come from satellite altimetry, a technique that measures tiny variations in the height of the sea surface. Although the ocean appears level to human eyes, gravity exerts a subtle influence. Massive underwater mountains pull slightly more water toward themselves, while deep trenches produce the opposite effect. By measuring these delicate differences, scientists can infer the general shape of the seafloor below. The resulting maps reveal major structures across the globe at a resolution of approximately 5 kilometers, which is about 3.1 miles. Smaller features disappear within that scale, remaining concealed beneath the ocean. To uncover those finer details requires direct acoustic multi-beam sonar surveys. Ships send sound pulses downward and measure the returning echoes, gradually building detailed maps with resolutions approaching 100 meters, which is about 328 feet. That level of detail is comparable to mapping available across much of Earth's land surface. Yet, despite decades of effort, less than 1/4 of the global ocean floor has been surveyed in this manner. The overwhelming majority still waits beyond the reach of comprehensive observation. Where these surveys have been completed, they reveal a landscape of astonishing complexity. Long chains of seamounts extend for thousands of kilometers. That is nearly 621 miles for every 1,000 kilometers within their length, tracing ancient volcanic pathways across the ocean basin. Vast collapsed calderas spread wider than entire cities, marking eruptions of extraordinary scale that unfolded beneath the sea. Immense lava fields blanket regions comparable in size to entire nations, preserving the layered history of countless volcanic episodes. Hydrothermal vent fields appear among this rugged terrain, each supporting living communities whose relationships are only beginning to be understood. One remarkable discovery rising from these surveys is Tamu Massif, located in the northwestern Pacific. Covering an area roughly comparable to the modern region of New Mexico, this immense shield volcano formed approximately 145 million years ago. Although scientists had recognized parts of the structure for years, its full extent was not confirmed until the early years of the present century, demonstrating how even colossal volcanic features can remain partially hidden beneath the ocean for generations of research. The living world has proven equally surprising. Since the first hydrothermal vent system was discovered during the late 1970s, researchers have documented more than 600 species previously unknown to science. Nearly every newly explored vent field has revealed organisms found nowhere else, suggesting that these isolated habitats have followed separate evolutionary paths for immense spans of time. Many scientists believe that only a small fraction of their total biological diversity has yet been described. Perhaps the greatest mystery lies deeper still, beneath the sediment and within the volcanic crust itself. There, microscopic communities persist without any dependence upon sunlight, drawing energy instead from chemical reactions between water and rock. Hidden throughout the ocean floor of the Ring of Fire, these unseen forms of life suggest that Earth's largest living habitat may also be its least explored, continuing its patient existence beneath a landscape that humanity has only begun to discover. Across the vast curve of the Pacific, cities rise where continents meet restless seas. Villages stand beside volcanic slopes, and generations have built their lives upon ground that is never entirely still. The Ring of Fire passes through or beside some of the most densely populated regions on Earth, including Japan, Indonesia, the Philippines, the western portions of the United States and Canada, Chile, Peru, and countless island nations scattered across the ocean. Altogether, An estimated 800 million people live within meaningful range of its earthquakes, tsunamis, or volcanic eruptions, making this immense geological system not only a natural boundary, but one of humanity's greatest shared neighborhoods. For thousands of years, the Pacific has offered fertile soils, abundant fisheries, sheltered harbors, and trade routes connecting distant shores. Those same conditions that encourage settlement were created by the tectonic forces beneath them. Volcanic ash gradually enriched farmland. Rising mountains redirected rainfall into productive valleys. New coastlines emerged through uplift, while others slowly descended beneath the sea. Human history became intertwined with geological history until neither could be understood entirely without the other. The archaeological record preserves this partnership with remarkable clarity. Excavations along many Pacific coastlines reveal repeating layers that resemble the turning pages of a very long chronicle. One layer contains homes, tools, pottery, and traces of ordinary life. Above it lies a blanket of tsunami, sand, or volcanic ash. Higher still appears another layer of homes and daily activity, built once again upon the same ground. Across centuries, and sometimes across millennia, communities disappeared and returned repeatedly, rebuilding where previous generations had lived, because the same landscapes that carried danger also continued to provide extraordinary opportunity. Few places illustrate this balance more clearly than the island of Java in Indonesia. More than 150 million people live upon an island comparable in area to the modern state of New York. Beneath that crowded landscape stand approximately 30 active volcanoes, each formed by the continuing descent of oceanic crust beneath the surrounding islands. During the eruption of Tambora in the early 19th century, an estimated 71,000 people lost their lives through the combined effects of the disaster. Ash and sulfur, released high into the atmosphere, spread around the globe, reducing average temperatures and contributing to widespread harvest failures across much of the northern hemisphere during the following year, remembered as the year without a summer. Yet the people living throughout the Ring of Fire have never faced these landscapes without knowledge or preparation. Japan has developed some of the world's most sophisticated earthquake-resistant building practices, tsunami warning systems, public education programs, and emergency planning. Similar efforts continue across many nations, where earthquakes and volcanoes are accepted not as distant possibilities, but as recurring features of ordinary existence. Scientific observation, engineering, and shared experience have steadily reduced risk, transforming lessons from previous disasters into stronger communities. Even so, the geological record offers a humbling perspective. Again and again, human planning has been shaped by the largest events preserved within memory, while the Earth preserves a memory measured across far longer intervals. Engineers responsible for the Fukushima nuclear power station believed they had prepared for the greatest tsunami supported by historical evidence. Designers of the coastal defenses in the Tohoku region trusted the limits established by recorded experience. Warning systems reflected the scenarios considered most likely from the available record. The Ring of Fire, however, continues to operate according to physical processes that recognize neither written history nor the boundaries of expectation. Across the immense sweep of geological time, civilization has learned to live beside this restless margin, adapting with every generation, while the deeper rhythms beneath the Pacific continue their patient work, unchanged by the passing of empires or the ambitions of those who call its shores home. Some of the most important evidence surrounding the Ring of Fire is neither buried beneath the sea nor locked inside ancient rock. It exists within memory, carried from one generation to another with all the strength and fragility that human history allows. The greatest challenge presented by this immense tectonic system is not simply understanding the geology itself. It is preserving knowledge across spans of time that greatly exceed the lifetime of any individual, any institution, or even many civilizations. For the Earth, an interval of 300 to 500 years is only a brief pause between recurring events. For humanity, it represents approximately 15 to 20 generations. Families change, languages evolve, governments rise and disappear, and written records are lost through war, disaster, or neglect. Even where stories survive, practical details often soften with time as living experience gives way to distant remembrance. The geological clock continues without interruption, while human memory must struggle to preserve lessons that may not be needed again for centuries. Along the Pacific Northwest coast, indigenous communities accomplished something extraordinary. The Huayat, the Quileute, the Ho, and other peoples preserved accounts of a tremendous winter night when the ground shook violently and the ocean advanced across the land. Their traditions spoke of villages destroyed by immense waves, and of survivors who endured because they had reached higher ground before the water arrived. These narratives remained part of community memory for roughly 300 years, carried through spoken tradition rather than scientific documentation, preserving essential details long after the original witnesses had passed from the world. For many years, researchers outside those communities regarded these stories primarily as cultural history. During the closing years of the 20th century, scientists began comparing them with entirely different forms of evidence. Historical records from Japan described an unexpected tsunami arriving without any locally felt earthquake. Along the Pacific Northwest coast, drowned forests preserved tree rings, marking the sudden death of ancient cedar stands as the land abruptly subsided. When these separate lines of evidence were brought together, they converged upon the same event. The oral traditions had accurately preserved the memory of a specific megathrust earthquake across 3 centuries, demonstrating that cultural knowledge and geological investigation could illuminate one another with remarkable precision. That discovery also revealed the deeper challenge facing modern societies. Hazard science depends not only upon measuring faults or monitoring volcanoes, but upon sustaining knowledge between rare catastrophes. Building regulations must remain effective across generations that never experience the disaster they were designed to withstand. Evacuation routes require continual maintenance even when decades pass without their use. Public awareness must survive long intervals during which ordinary life naturally encourages the belief that the greatest danger belongs only to the distant past. The coastline of Japan offers another enduring expression of this struggle. Scattered along certain shores stand ancient tsunami stones, placed by survivors who wish to leave guidance for descendants they would never meet. Their inscriptions warn future generations not to build homes below the elevation marked by the stones. Some of these monuments have remained in place for approximately 600 years. During the Great Tsunami that struck in the early years of the present century, the water in several locations rose almost precisely to the height indicated by the highest of these markers. Yet many modern communities had expanded well below those elevations, placing homes, roads, and critical infrastructure within areas earlier generations had deliberately avoided. Between the enduring record preserved by the earth and the shorter memory carried by civilization lies a distance that cannot be measured in kilometers or years alone. It is measured in the gradual fading of lived experience, in the difficulty of maintaining vigilance across peaceful centuries, and in the continuing effort to remember lessons that geology patiently repeats long after the voices of those who first learned them have fallen into history. Far beneath the broad expanse of the Pacific, where no horizon reveals the motions below, the planet continues a rhythm older than mountains, oceans, and every living creature that has ever crossed its surface. Some have described the Ring of Fire as a great time bomb, an immense system gathering strain until the next destructive release. The image is compelling, yet it suggests something with a beginning, an ending, and a final moment that can be counted toward. The Earth offers no such certainty. A true time bomb waits for a single detonation. The Ring of Fire does not wait. It has no final hour because it is not a temporary condition of the planet. The immense forces that shape it, the descent of oceanic plates into the mantle, the creation of fresh seafloor along distant ridges, and the slow circulation of heated rock deep within the Earth, are among the fundamental processes that have sustained this world for hundreds of millions of years. They continue today with the same patient persistence, indifferent to calendars, civilizations, and generations. The great eruption of Hunga Tonga in the early years of the present decade did not represent an exception to the rule. The immense Valdivia earthquake during the 20th century was not an exception. The Cascadia rupture remembered across the Pacific was not an exception. Each belonged to the same uninterrupted sequence, separate moments within a geological story that has continued for approximately 700 million years. Long after every modern city has changed beyond recognition, those same processes will still be guiding continents, raising volcanoes, and drawing ancient seafloor into the depths beneath the oceans. Yet the Ring of Fire has never been defined by destruction alone. Along its spreading ridges and volcanic landscapes exist hydrothermal vent communities sustained entirely by energy rising from within the Earth. These remarkable ecosystems require no sunlight to flourish. Instead, microscopic organisms draw nourishment from chemical reactions released by heated rock and mineral-rich water. Evidence suggests that such forms of life have existed for at least 3,500,000,000 years, long before widespread photosynthesis transformed the atmosphere. They preserve a glimpse of an ancient world whose conditions may resemble the earliest chapters in the history of life itself. Those same geological processes have shaped nearly every Pacific shoreline. They lifted islands from beneath the sea, renewed soils through volcanic ash, supplied minerals that support marine ecosystems, and participated in the long cycling of carbon dioxide between the atmosphere, oceans, crust, and mantle. Across immense spans of time, that circulation has helped regulate conditions suitable for life. The same forces also guide scientific efforts to understand whether similar environments on distant worlds might provide opportunities for living systems to emerge beyond our own planet. Nearly 800 million people now live within reach of the earthquakes, volcanoes, and tsunamis generated by this immense tectonic network. Their homes stand upon land created by the very forces that occasionally reshape it. The relationship is neither simple nor one-sided. It is an enduring partnership between civilization and an active planet whose surface has never settled into permanent stillness. Every generation inherits landscapes formed through countless earlier cycles of uplift, eruption, erosion, and renewal. Perhaps the deepest meaning of the Ring of Fire lies beyond the language of catastrophe. It reminds us that Earth is not a finished creation resting in perfect balance. It remains a world under construction, continually building, breaking apart, and building once more across intervals so vast that human history occupies only the briefest instant within them. The ocean above the ring of fire appears calm tonight. Beneath that surface, the plates continue their ancient journey. They have never stopped, and the steady heartbeat of the planet goes on.